And suppose that we have a function, and I'm not going to have a formula for the function. I'm just going to, give you what happens, what the outputs are of the function every hour. So some function y equals f of x gives the total number of miles driven, so we're on some road trip somewhere, as a function of the number of hours. Often I would call it t, but here I think I'll just call it x, since we left home. Okay, so the independent variable is the number of hours since we left home. F of x is the number of miles we have driven after that many hours. And, at, every hour we just, look and see how far we've driven. So after 0 hours, we have not driven any miles. We're still at home. After 1 hour, let's say we only drove 30 miles because, we're trying to get out of the city and, whatever, stop and go traffic. After another hour, we've gone a total of 70 miles. So during the first hour, we went 30 miles. During the second hour, we were able to go 40 miles. Going a little further during the second mile. So we're certainly not going at a constant speed, okay? Let's say after 3 hours, we were able to go 130 miles. So during the third hour, we were able to go 60 miles, okay? After 4 hours, we've gone 190 miles, okay? So, that's what we know. Okay, so what we want to do is find our average speed on various intervals of time. So initially, find the average speed during the first hour. Okay, so during the first hour. Now just for future reference, that means from x equals 0 to x equals 1. That's the first hour, okay? All right, so speed is the total miles driven divided by the total time, like miles per hour, okay? So my average speed on that first hour, from x equals 0 to x equals 1, is the total distance in miles that we were able to drive divided by the total time. Now, during the first hour, how many miles were we able to drive?
1 hour.
30, right? We had driven 0 miles at the beginning, and then after 1 hour, we had driven 30 miles. So our total distance is, I'm just going to write this, 30 miles minus 0 miles, which is, of course, 30 miles. Over what time period?
1 hour.
1 hour. And I'm just going to write it this way. 1 hour minus 0 hours. So in other words, 30 minus 0 is 30. Total distance of 30 miles in a time period of 1 hour. So in other words, 30 miles per hour. You can write MPH, but I kind of want to emphasize that there's miles on top and hours on the bottom. Okay? Okay, now let's find my average speed over different time intervals. Say I want my average speed during the first 2 hours. So in other words, from x equals 0 to x equals 2. Okay, so not just the second hour, but during the first 2 hours. Okay, so again, my average speed is my total distance in miles divided by the total time. Okay, so how far did I go during the first 2 hours? Okay, so 70 miles, right? And let's just say 70 miles minus 0 miles, because after 0 hours I had gone 0 miles. Over what time period?
2 hours.
Right? So 2 hours minus 0 hours. Or in other words, 70 miles. I want a distance of 70 miles in 2 hours. So my average speed on that 2-hour time interval is, 35 miles per hour. Okay, so, looks like during the second hour we were able to speed up a little bit because my average speed over the first 2 hours is bigger than my average speed during the first hour. Okay. Let's find the average speed during the last 2 hours. In other words, from x equals 2 to x equals 4. Okay, so again, average speed is the total distance in miles divided by the total time in hours. Okay, so from x equals 2 to x equals 4, how many miles was I able to, go? Yeah, so I was able to go 70 miles after 2 hours and then 190 miles after 4 hours. So I was able to go a difference of 120 miles, but let me write it. 190 miles minus 70 miles divided by what amount of time? Yeah, so 4 hours minus 2 hours, or 2 hours. So I want a distance of 120 miles over a 2-hour time period. So during that 2-hour time period, on the average, I was going 60 miles per hour. Okay, so definitely we were able to speed up during the last part of the trip. The first hour we were only going 30 miles per hour, now we're going 60 miles per hour on the average from, during the last 2 hours. Okay, now I want to look at this, quantity here, this 190 miles minus 70 miles over 4 hours minus 2 hours, and, write it in a way so that we can generalize, okay? Now, okay, I'm saying that my function, I have this function, I'm calling it f of x, so the y value is f of the x value. So in other words, f of 0 is 0, and f of 1 is 30, and f of 2 is 70, and f of 3 is 130, and f of 4 is 190. Okay, so I want to look at the average speed from x equals 2 to x equals 4 is, okay, let me just write this, so, 190 miles minus 70 miles over 4 hours minus 2 hours. Okay, now I want to write these using, the 190 and the 70 as function values, y values. So 190 miles is what? How could I write that as a function of something? That's f of 4, right? 190 miles is f of 4. How about 70, then I'm a minus. How about 70 miles?
Two.
That's f of 2. And then the denominator, I'm going to take off the units, is 4 minus 2. Okay, all of these average speeds are of this form. F of some number minus f of some other number divided by that first number minus that second number. So this kind of expression seems to be important. Okay, it gives us the average speed, okay, that we're traveling on this trip in terms of the function f of x. Okay, so let's generalize, okay, to the topic of this section. Okay, so definition. So let's let y equal f of x be some function. Okay, then we're going to define the average. Now, in our case, it was average speed, but it depends on what the function gives you. It might be the average temperature on a certain time period, or the average cost of something you're buying, whatever it is. It's a rate. Here the units of the rate are miles per hour. Rates are always of the form something per something else, and we've always got a fraction. And I write this out in general. So, in general, this is called the average rate of change of f. The average rate of change of f from, there's always some x value that you're starting with, say from x equals a to x equals b is, okay. Now, when we wanted the average speed from x equals 2 to x equals 4, then we had f of the bigger number, okay. And when I write from x equals a to x equals b, I'm really assuming that a is smaller than b, okay, because you're going from here to here. Doesn't really matter, but it makes more sense. So f of the endpoint, f of the bigger number, minus f of the smaller number, divided by the bigger number minus the smaller number. So f of b minus f of a all over b minus a. So that is the definition of the average rate of change of a function from x equals a to x equals b. Now, okay, we know what this means in our particular case, okay, when the numerator is measured in miles and the denominator is measured in hours, then this is the average speed measured in miles per hour. But what does this mean on a graph of the function? Okay. So what does this mean graphically? Okay, so I'm just going to draw some arbitrary picture of some function. I mean, of course, it doesn't have to be in the first quadrant, but, you know, if it means something, probably x and y are positive. So let's say here's the graph of y equals f of x, okay? And then we're going from x equals a to x equals b, okay? Now, what are the coordinates of the point corresponding to x equals a? So a comma f of a. Okay, and what are the coordinates of the point on the graph corresponding to x equals b? So b comma f of b. Now here we have 2 points on a graph. One of the coordinates is a comma f of a, the other coordinate is b comma f of b. Now, what does f of b minus f of a over b minus a mean with respect to these 2 points? What does that give us about these 2 points? Yes, the slope of the line passing through those 2 points. Because what we're doing is we're taking this y coordinate and subtracting that y coordinate and dividing by this x coordinate minus that x coordinate. Y sub 2 minus y sub 1 over x sub 2 minus x sub 1. Okay, so that average rate of change is nothing more than the slope of the line that passes through those 2 points. I'm just going to draw it. Now, you know, probably the graph itself is not a line. You know, it's probably some curve. I mean, it could be a line, but I'm certainly not assuming it is. Okay, but if you draw the line passing through those 2 points, then the slope of that line is that f of b minus f of a. Okay? Down here. So, the slope of the, now I'm going to give you a word that people use, comes from geometry, it actually comes from circles. You know how when you have a circle, and it works for any curve whatsoever, and if you have a line that simply touches the circle in 1 point, so the line and the circle just intersect at 1 point, what is that kind of a line called?
Tangent.
A tangent line, right? That's one of the problems on the test. If, however, you have a line that intersects a circle, and in general any curve, that intersects, the line and the circle intersect in 2 points. Anyone know what that line is called? It's called a secant line. A secant line is just a line that intersects, back in geometry, a circle, but in general, a line which intersects a curve in 2 points instead of just 1 point. So people generally talk about this line that intersects the curve in 2 points as a secant line. So the slope of the secant line passing through the know, 2 points, you know, A comma F of A and B comma F of B is, you know, maybe let's just remember our slope formula. If my points are x1, y1 and x2, y2, my slope is y2 minus y1 over x2 minus x1. But, okay, let's say this one is x1, y1, and this one is x2, y2. Then y2 is f of b, y1 is f of a, over x2 minus x1 over b minus a. Okay, so in other words, the slope of that secant line is the average rate of change of the function from x equals a to x equals b. Okay, let me just go back and label that here. So here, the slope of this line is my f of b minus f of a over b minus a, my average rate of change. So let's just go back and kind of look at our function as much as we can graph it. We don't have the formula, but we have 5 points on the graph. Maybe I'll write something down there. I'm not going to bother with graph paper because I'm just doing this roughly. Okay, so the x-axis is the number of hours and the y-axis is the number of miles. And let's see. I'm just going to do 1, 2, 3, 4. And let's see, my y values maybe every 10 units. Try to get up to 19. It's 50. Okay, good enough. All right, so if I make a sketch of this graph, I have 0, 0. After 0 hours, I went 0 miles. After 1 hour, we went 30 miles. After 2 hours, we went 70 miles. After 3 hours, 130 miles. And after 4 hours, 190 miles. Now, I mean, who knows what the graph really looks like in here, but let's just assume that it's sort of a curve. Pretend, anyway, some sort of a curve. Okay. Now, if you want to know how fast you were going, like on every single, hour interval, you would just need to know the slope of the line, the secant line passing through those 2 points, okay? So if say I want to know, how fast I was going during the first hour, okay, it's the slope of that secant line. And, we already calculated that. That slope is 30 miles per hour. Okay? I didn't calculate this, but if I want to know how fast we were going during the second hour, just from time 1 to time 2, or 1 hour to 2 hours, okay, then the slope of that line is how fast we were going, and it turns out to be 40 miles per hour. Now, even without doing the calculations, okay, just by the slope and the steepness of the line, you can tell whether you were going faster during the first hour or faster during the second hour. I mean, my graph isn't perfect, but which line is steeper? The line from 0 to 1 or the line from 1 to 2? The line from 1 to 2. Even if I didn't do the calculations, this line is steeper than that line. So that means that during the second hour, okay, I had speeded up. My speed, my average speed is more than my average speed during the first hour. Okay, and what about during the third hour? I didn't actually calculate it, but is that line steeper or less steep than the line that I had just drawn, the sort of pinkish purple line? It's steeper. Okay, so from time 2 to time 3, okay, I went faster than from time 1 to time 2. And you know, you can calculate the slope if you want. It's what? 130 minus 70 is 60 miles per hour. Okay, and what about the last interval? Okay, from time 3 to time 4. I don't have the right one. Looks like the slope is the same. I mean, you know, you really have to do the calculations to see that, but you know, looking at the graph, it kind of looks like that slope is the same as the slope from time 3 to time 4. And, you know, if you do the calculations, yeah, we got 190 minus 130 is, again, 60 miles per hour. Now, in this graph, the slopes are getting bigger. Okay, in calculus you study slopes. Basically, that's what the first half of calculus is all about, slopes. And so you'd look at this curve and you'd say, oh look, those slopes are getting bigger. Okay, at least for a while they're getting bigger. Okay, and that, you know, is given a certain name, and, you know, graphs where the slopes are getting bigger is given a certain name, graphs where the slopes are getting smaller is given a certain name. If the slopes are getting bigger, we say that the car is accelerating. If the slopes are getting smaller, we say that the car is decelerating. You know, so there's all this physics that comes in. Anyway, so you can just look at the slope of the secant line between 2 points on the graph, okay, regardless of whether the graph itself is aligned, which it probably isn't. That slope gives you, you know, if you got miles on the y-axis and hours on the x-axis, that slope gives you the average speed in miles per hour. All right. Now, let's just do some calculations with just some regular old functions, just to, you know, not necessarily functions that mean anything, at least for a little while. So just practice calculating this average rate of change of a function from some x value to some other x value. All right, so. So let's let f of x be the function. X squared minus 4, okay, f of x is x squared minus 4. And let's calculate some average rates of changes on certain intervals. Okay. So, find the average rate of change of this function f from x equals 0 to x equals 3. Okay, so let's just do the calculations and then, see what it means. Okay, so by definition, the average rate of change of some function from x equals a to x equals b, here a is 0 and b is 3, okay, is f of the number after the word 2 minus f of the first number, so f of 3 minus f of 0 over 3 minus 0, okay? So sometimes people say ARC for average rate of change, from x equals 0 to x equals 3, okay, is f of 3 minus f of 0 over 3 minus 0. Okay, and right now, we're not worried about units, we're just gonna get a number. Okay, so what's f of 3?
3 squared minus 4.
So 3 squared minus 4, 9 minus 4, or 5, minus, what's f of 0?
0 squared minus 4.
0 squared minus 4, or negative 4, over 3 minus 0, which is of course 3. Okay, so we got 9 minus 4 is 5, minus negative 4 over 3 minus 0, or in other words, 5 plus 4 over 3, or 9 over 3, or 3. Now, let's see what that means with respect to the graph of this function, okay? What does the graph of f of x equals x squared minus 4 look like? We don't actually know about the shifting, but where's the y-intercept?